All right, I decided that our homework is going to be to just finish our notes going through this so that tomorrow in class we can work through some problems dealing with this equation in the right-hand rule. So please take the time to watch this video, take notes on it. If you did not draw these pictures in your notes today, I didn't notice many of you drawing, please do so. So ultimately, this is the main thing we are taking a look at here, that one, I can create a stronger magnetic field by changing the shape of my wire, right? So by looping it, I now create two magnetic fields on the inside that are going in the same direction because the current is going in the opposite direction. So two magnetic fields are going to add up to give me a stronger magnetic field. And if I loop it again and I loop it again, these magnetic fields add up. Will eventually create a magnetic field that looks just like a bar magnet. That is what we call an electromagnet. So I didn't really write that into your notes, but this is called an electromagnet. So on Thursday and Friday of this week, I'd like to do a lab with an electromagnet. It's pretty cool to try to see what does that magnet, the strength of the magnet depend on. In the meantime, if it is true that that creates a magnetic field, then it itself acts like a magnet and should experience a force when placed in a magnetic field. So it's no different than two magnets, excuse me, being placed in front of one another. Being placed near one another, attracting and repelling one another, the same thing is going to happen on a wire. So a wire placed in a magnetic field will experience a force due to the field it's placed in. So that's a key word, placed in, right? So here's our equation again. We ended with quickly taking a look at the right-hand rule. We'll practice again. So some things to remember when you're doing the right-hand rule is current always flows positive to negative. Right? Magnetic fields go north to south. Whoops. And that's the benefit of a horseshoe magnet. So when we started all this, I had you draw pictures of magnets. What a horseshoe magnet does is it's curved like that with the north and south like this. And what that does is within this space, you then have a straight magnetic field rather than in a bar magnet as you go from north into south. Everywhere your magnetic field is curved going around that. So I can create a nice straight magnetic field by using a horseshoe magnet or setting up two magnets like we have right here in this example problem. We have a north and a south. Okay. All right, let's try another one. What happens if I put my magnets like this, practicing the right-hand rule, and that's my north pole, and this is my south pole, right? And I take a current, so, and I send the current like this. If this side is positive and that side is negative. The question would be, what is the direction of the magnetic field? I'm sorry, not the magnetic field, but the force. What is the direction of the force on the wire? And then if B equals, let's say, 2 times 10 to the minus 4th Tesla, and current is equal to 10 amps, what is the magnitude of the force on the 1 meter length of wire? So if we do this as an example, right? So first of all, you have to ask yourself, what's the direction of current? Current will go from positive to negative. So it's going to be going to the left. The magnetic field is going to flow north to south. So this is going to be your B field, right? So that's your B, and this is your I. The question is, what is the direction of the force? So for this one, it's a little tricky. You're going to put your thumb, I guess I'll turn my camera back on. So on this one, you're going to put your thumb in the direction of current, right? Fingers in the direction of the magnetic field, which is down. So it's going to be going down. Thumb in the direction of current, fingers go down. Palm of your hand is pushing towards you or out of the page. So in this case, this wire is going to want to pop out of the page. So again, thumb in the direction of current, fingers are flat and they must point. Thumb has to stay that way. Rotate your fingers until they are going down. Palm of your hand points towards you. Okay. So with the palm of your hand pointing towards you, you would say the direction of the force is to come out of the page. So our force, I want to draw a circle. It's coming out would be a dot. That's the direction of the force. It's going to want to come out of the page. As far as its magnitude, right? So we would say, what do we know? B is equal to 2 times 10 to the minus 4th Tesla. I is equal to 10 amps. And the length of wire is 1 meter. So the force has a magnitude of B, I, L. So it is simply 2 times 10 to the minus 4th Tesla times a current of 10 amps times the length of wire of 1 meter. So that force equals, should come out to be 2 times 10 to the minus 3rd newtons would be the units. And if I were to put a direction to it, we would say out of the page. So notice I added my vector quantity on top to say it's a vector. My direction is out of the page given by the right-hand rule of my picture. And the magnitude is 2 times 10 to the 3rd newtons. Okay, so that's placing a wire in another magnetic field that exists because of 2 magnets. Well, you could have a magnetic field as a result of 2 wires. So 2 wires placed next to each other. If I have wire A, right, like this, next to wire B, like this, these 2 wires will both produce a magnetic field, and therefore, as I bring B near A, it will be placed in the magnetic field of A. So we would say here that B will experience a force due to being placed in A's magnetic field. So the force on B is going to be due to the magnetic field of A times the current through B times the length of B. So putting these subscripts on there, I want to clarify, what would you put in here? You'd have to find the magnetic field of A, but everything else has to do with the object itself being placed in there, its current and its length. Whereas if I take a look at A, if A is brought in near B, A will experience a force due to being placed in the magnetic field of B. So what would that equation look like? You think about it before I write it. The force on A is going to be magnetic field of B, current of A, length of wire of A. So the question becomes, what's the direction of the magnetic field? What would be the direction of the force? Because we want magnitude and direction, right? What would those two wires do when placed near each other, and so on. So here's an example problem typed up here to take a look at. If I have two wires, both of length 50 centimeters, and they're placed 30 centimeters apart, one carries a current of 10 amps, while the other a current of 7 amps. If the current is in the same direction, what is the magnitude and direction of the force on each wire? So if I go back to my whiteboard, using that same picture, we can say, okay, they have a length of 50 centimeters. So we're going to give them a length. They both have a length equal to 50 centimeters. They are placed 30 millimeters apart. One has a current of 10 amps. We'll let that be for A. And the other has a current of 7 amps. All that matters is that current is going in the same direction for both. So I'm just going to draw that like that, right? So putting some numbers to this, they have the same direction of current. So remember, A is placed in the magnetic field of B. So what is going to be the magnetic field of B? So let's take a look at A first. If I take B, current going up, right? When I grab this wire and I place my thumb and I grab it, on the right side I have to go in, and on the left side I have to come out, right? So this one is going to have a magnetic field, right? So I'm going to go like this. That's going to circle around in this direction, which means I have dots on this side all the way over across A, right? That's due to the magnetic field due to B, and it's going to have X's on its right side. Are you okay with that? Thumb goes up and I grab it. So only worry about A. Pretend that B is not even a wire that is present. So if we just take a look at A, right? If I look at the wire of A, what I know about A is that it has a current of 10 amps. It has a length equal to 50 centimeters, which is 0.5 meters. And the magnetic field that it's placed in is due to B. So I have to go over here. What do I know about B? B has a current of 7 amps, has a length equal to 50 centimeters, which is 0.5 meters. It's placed in the magnetic field, placed in is due to A, right? The field made by B, right, is going to equal mu 0 I over 2 pi r. This is going to be IB, and this R is, well, where are you worried about it? I'm worried about the magnetic field of B 30 millimeters away, right? So if I go back to my problem, it was 30 millimeters apart. So the R value that I really want here is 30 millimeters, which is 0.03 meters. So what I want to do is find the magnetic field that B creates, which would be 4 pi times 10 to the minus 7 Tesla meters per amp times 7 amps all over 2 pi times 0.03 meters. That'll give me the magnetic field of B located where A is. And that's what I'm going to use over here under A. So everybody calculate that. Oh, Oh, nope, I keep wanting to share. Sorry, sorry about that. So I get that magnetic field to be 4.67 times 10 to the minus 5 Tesla. Okay? Sorry. That's the field then that I'm going to put up here. So the B that A is placed in, magnetic field of B, is 4.67 times 10 to the minus 5 Tesla. Right? What I want to do then is also find the magnetic field to A. So now I want to do the same thing over here at A, and I'm going to use that field over here. So the field made by A comes over here. So the field of A is equal to mu 0, current that's in A, all over 2 pi, distance away from A. So it's going to be 4 pi times 10 to the minus 7 Tesla meters amps times 10 amps all over 2 pi times 0.03 meters. So again, here your R is 0.03 meters. So the amps cancel. 2 pi becomes a 2. So your magnetic field at A equals, find that magnetic field, punching that into your calculator. For that one, I get 6.67 times 10 to the minus 5th Tesla. That's the magnetic field that I want to use up here, that B is placed in, 6.67 times 10 to the minus 5 Tesla. Okay, that magnetic field, so that's the strengths of those magnetic fields. That's the magnetic field due to A, and that's the magnetic field due to B. So again, just to remind you all what you're doing, right? So each wire creates its own magnetic field. That's what we've calculated here. The other wire gets placed into that one's magnetic field. So what we want to do now is, what is the force on A due to being next to B, and what's the force on B being next to A? So we want to find those two forces, magnitude and direction. So we have the magnetic field created by A and the created by B, the magnitudes of them. For B, we recognize that on the left of it, it's going to have dots, which means the magnetic field is coming out, right? And on the right, it's going in. So if we only look at A, then we can isolate A and say that A, right, has a current in it, consistent in my colors here, that is going up, but it's being placed in a magnetic field that is coming out of the page, right? So its magnetic field is coming out of the page. So the force on A, I just want to look at A, is going to be equal to the magnetic field it's placed in, which is the force due to B, or the magnetic field due to B, the current in A, and the length of wire of A. So the strength of that magnetic field, I'm going to use 4.67 times 10 to the minus 5 Tesla. But the current is going to be 10 amps and the length 0.5 meters. This force comes out to be in newtons, and that has to do with the base unit of a Tesla. Get rid of the amps and the meters and so on. We come up with units of newtons, and I get 2.33 times 10 to the minus 4th newtons. That is the magnitude. Its direction, I'd have to put my thumb up and the fingers would come out of the page. So again, to show that to you, to find the force on A, thumb goes up, fingers would have to be turned to come out of the page towards me, right? So thumb is going to go up and I'm going to go out of the page. Palm of my hand is going to push across to the right. So the force on A is going to be going to the right, or 0 degrees. So the magnitude of the force is 2.33 times 10 to the fourth. The direction is to the right, or 0 degrees. If we go back up and we take a look at B, right? B is placed in the field that A creates. A is going to create the same kind of magnetic field where it's going to be having X's on its right and dots on its left. So around it, its magnetic field looks like this, the same as B. But since B is on its right, that means B is placed in a magnetic field that's going into the page. So if I only look at B, and I think of the wire of B, current on it is going up, but it's placed in A's field, which is going into the paper. The strength of that field is going to be the force on B is going to be the magnetic field due to A, current of B, length of B. So the magnetic field of A was 6.67 times 10 to the minus 5 Tesla. B has a current of 7 amps and a length of 0.5 meters. When you plug that in, you will find that you come up with the same exact magnitude of force, 2.33 times 10 to the minus 4th newtons. However, its direction is such that you place your fingers to go up, your thumb to go up and your fingers towards the paper. So thumb goes up, fingers go into the paper like that. Palm of your hand would point to your left. So thumb up, fingers into the paper. Whereas A, my thumb was up and fingers were out of the paper. So for B, the force on B is going to be to go to the left this way. 180 degrees. That means two wires that are carrying current in the same direction will have forces on them to cause them to attract. Sorry. They will attract. Okay, so summarizing again, two wires, because a wire itself creates a magnetic field, another wire placed next to one wire will also be attracted or repelled from it because it itself creates a magnetic field. The two magnetic fields affect one another just the same as two magnets would. A gets placed into B's field, B gets placed into A's field. So first you have to find the field created by each wire, and then the force on the wire is the result of being placed in the other one's field. In this case, two wires carrying current in the same direction, the force is to cause them to attract. Excuse me. Then you can imagine if I just switched the direction of current, these two wires would repel. Okay. Well, hopefully that you can go back through. Keeping in mind, I mentioned on the video that you do have a textbook that contains all this information, and I believe those are that is chapters 20 and 21 in your textbook. To refer to that again. All right, so take notes on this information. This was the problem again that we just worked out. If you want to take a screenshot or a picture of that, or write that in your notebook as the example that we just did. Tomorrow in class, we will go through solving similar problems using the right-hand rule and calculations. So no UT Quest.